Alright, hello everyone. I hope you guys are doing good. So, today I'll be discussing the solutions to Codeforces Educational Round 119. This round was held yesterday, and let's begin by talking about the round. Well, the difficulty level of the problems was good enough. There was a gradual increase in the difficulty of problems, but one thing that was not quite good about this round was the order of the problems. Like they were very mixed up, and the difficulty rise was not linear from A, B, C, D to E. Right. Other than that, the round was like not very bad. The problems were good, but according to me, if you ask me to sort the problems based on the difficulty levels, I would have preferred an order like this: B, A, E, D, and C. Like out of A to E, I found C to be the most difficult problem, mostly because of implementation details. But yeah, that was a more optimal order according to me, right? Anyways, I will be discussing the first five problems from A to E. So yeah, without any further ado, let's start with the solution to problem A. So we have n positive integers a1 to an arranged in a circle, and for each pair of neighboring elements, we write down a letter basically, and if ai and ai plus 1 are equal, we write down e, otherwise we write down n. And we have lost the array, and we also don't know whether the information is correct or not, whether the written information we have is correct or not. And we need to find out whether it is possible to have such an ordering or not. We have been given with an ordering of e's and n's, and we have to answer whether a particular ordering is possible or not. If it is possible, we need to output yes, otherwise we need to output no, right? So yeah, that's the problem, and let's start with the solution. And I'll begin by making a claim, and the claim is actually the entire solution. And my claim is that if there is exactly one n, then answer is going to be no, otherwise the answer will always be yes. Then answer is no, otherwise the answer is always yes. And let's see why this is true, right? Let's try to see how things will be here. So what we have is we have n people, right? So we have n people like this, and they all are seated in a circle. So let's just say that the nth and the first person are seated adjacent to each other here. And now let's see what's happening, right? So what if there is exactly one n? If there is exactly one n, let's say the n is somewhere here, and all the others are just e's, right? So let's say that all the others are e's. Yeah. So if all the others are e's, I know that every element here is going to be the same, right? So I know that every element in this particular prefix is going to be the same. Starting from this element down to this element, all the elements are going to be the same, and also all the elements here are also going to be the same, right? But one thing that I am forgetting here is that a1 and an are also adjacent. Okay, so let's say that without loss of generality, all the elements here are 1 and all the elements here are 2. Now I know that this is also an e, right? So if this is an e, I know that element n and n plus 1 have to be the same, but according to what I've written here, element n is 2 and element 1 is 1, and an has to be equal to a1, which is not the case here. So obviously if there is exactly one n, the answer is no. So this is very well proved here. But what if there are more than one n's, right? I also have to prove that if there are more than one n's, then the answer is always going to be yes. And let's see how that is working out. So we are basically dividing all the elements into groups, right? That is what we are doing here. So let's say I get the first n here, and I get the second n here. Then I know that all the elements here are the same. All the elements here are the same, and all the elements here are the same. But now there is no compulsion for me, right? I can mark all the elements here as 1, all the elements here as 2, and then I can again switch back to 1, right? I can always do that. And here you can pretty easily see that all the conditions are being satisfied. A1 is also equal to an, and there is no other restriction for me to follow. And so if there are more than one n's also, I can just use the same argument and do a pretty similar construction and come back to 1 once I'm in the last group, right? So that will guarantee that a1 is equals to an, and there are no other restrictions for me to follow, right? So yeah, I have essentially proved that if there is exactly one n, the answer is always going to be no. Otherwise, the answer will always be yes. So that pretty much sums up the problem. The code is also pretty simple. You just count if the number of occurrences of n in the string is 1, then the answer is going to be no. Otherwise, the answer is going to be yes. And you print the answer. Right? So that completes the solution to problem A. Let's move on to the next problem now, problem B, which was somewhat easier than problem A, or maybe very, very similar. So let's see what we have here. So we have a rectangle with opposite corners at 0, 0 and w, h, and the sides of the rectangle are parallel to the x and y axes on the plane. And we have been given with some lattice points, and all of these points lie on one of the sides of the rectangle, and we also know that we have been guaranteed that we'll be given at least 2 points on each side of the rectangle. And our task is to choose 3 points from all the points that we'll be given, such that exactly 2 of them belong to the same side of a triangle, and the area of the triangle formed by them is the maximum possible. I'm sorry, the first point is that exactly 2 of them belong to the same side of the rectangle, and the area of the triangle formed by all the 3 points is the maximum possible. Right. The input is something like this. First of all, we will be given with a w and h, and then first of all, 2 lines will follow. The first line will be the description of all the points which are on the lower horizontal side. Then we'll be given with all the points which are on the upper horizontal side. And then in the next 2 lines, first of all, we'll be given with all the points which are in the left vertical side, and then we'll be given with all the points which are on the right vertical side, right? So this is how we have been given with the input, and we need to find out 3 points such that 2 of them belong to one side and 1 of them belongs to some other side, and the area of the triangle formed by the 3 points is the maximum possible. A very easy observation here. Let's see what that is. Okay, so we are at problem B now. So we have been given with a triangle, with a rectangle here, and at least 2 points on each side, right? So we have been given with few points on each side, which are at least 2. Right? So this is the situation that we've been given with. Right? So we need to choose 3 points here, and 2 of them have to belong to the same side. So obviously we can iterate on which side the 2 points belong to, right? That's one thing we can do. And before that, we need to maximize the area of the triangle, right? So we need to maximize the area of the triangle formed by 3 points such that 2 of them lie on the same side. Alright, we know that area of a triangle is equals to 1 by 2 times base times height, right? And also we have to output twice the area of the triangle, so we can just get rid of this half. So we need to maximize base into height, right? So let's just say that we choose the side on which we have 2 points to be this particular side, the bottom side, this one, right? So if we choose this as the side which has 2 points, first of all, I need to maximize my base, and second of all, I need to maximize my height. If I'm able to do that, I am sure that I will get the maximum area. So one thing which is guaranteed is that I will get more area if I choose 2 distant points than if I choose 2 nearby points, right? So if I choose these 2 endpoints as my points, so this point and this point, then I'm guaranteeing that I'm having the maximum base, right? I need to maximize my base and I need to maximize my height. These are the only two conditions that I need to follow, that I need to satisfy, right? So I need to maximize my base, and the way to do that is to choose the two most distant elements, and the most distant elements are nothing but the leftmost and the rightmost elements, right? So it makes sense to choose these two elements, and no other pair will give me a greater area, right? So yeah, one thing is that whichever side you choose, you take the 2 points which are most distant from each other, which are as far as possible from each other, and the way to do that is to take the minimum point and the maximum point, right? Okay, so I have picked these 2 points. Now what about the third point? Another claim is that I know that this particular length is h, so this length is h and this length is w, right? So let's say I choose a point in the vertical side, right? So let's say I choose this point, right? Then the triangle which I am forming is something like this, and the height of this triangle is going to be this length, and I know that this length is strictly smaller than h, right? And what if I choose a point here on the opposite horizontal side? Then the triangle which I end up with is this one, and its height is going to be capital, its height is going to be h, right? And this proves that it is always beneficial for me to choose a point which is on the opposite side, and it doesn't matter which point I choose because the height is still going to be h only, right? So I come up with a pretty simple algorithm. For any side, choose two most distant points and any other point on the opposite side. So just do this for all the 4 sides and take the maximum value that you'll get, and that will surely be your answer. And I have already proved this, right? So if you are currently on a horizontal side, then the area you'll get is the distance between two most distant points multiplied by h, and if you are on a vertical side, then the area you'll get is the distance between the two most distant points multiplied by w. So you will get these 4 values, and at the end of the day you need to take the maximum of these 4 values, and that pretty much sums up the problem. So let's just have a look at the code. So pretty simple. You take these 4 values first of all, and the first value is x1 of k1 minus x1 of 1 times h. This is when I am at the base. The second value is x2 of k2 minus x2 of 1 multiplied by h. This is when I am at the topmost horizontal side. And then the other two values are when I am at the vertical sides, y2 of k4 minus y2 of 1 into w, or y1 of k3 minus y1 of 1 into w. Here k1, k2, k3, k4 are the sizes, are the number of points that I have on the respective sides, right? Alright, so this is it for problem B. Pretty easy here up till now. So let's now move to the difficult ones. So I'll start with C now, even though it is really complex, the implementation part especially. So yeah, let's start with problem C now. Okay, so let's see what this says. So we have an integer k and a string s that consists of only characters a and asterisks. So we have a string which contains only a's and asterisks, and also we have an integer k, and each asterisk can be replaced by several occurrences of the letter b, and these number of occurrences are limited from 0 to k, and k is a constant, right? So for any asterisk we can choose the number of b's that we want to put there, but the number of b's can only be from 0 to k, right? And once we do that, the replacement of the string is called the BA string. The new string which we get is called the BA string. And what we need to do is we need to find the xth lexicographically minimum BA string that we can form. Right, that's our task. So out of all the BA strings that can be formed from the string that is given to me, I need to output the xth lexicographically smallest string. Also, the constraints are important here. That is, the value of n is up to 2000 and the value of k is also up to 2000. So that seems relevant to me. And x can be up to 10 raised to the power 18. Also, they have also guaranteed us that the number of BA strings that can be formed from the input string are greater than equals to x, right? So x doesn't exceed the total number of BA strings that can be formed, right? Yeah, so this is the problem. We need to output the lexicographically minimal string at the xth position, right? So let's see how we can solve this problem. So I'll try to be as clear as possible. This is a bit tricky. So yeah, I hope you guys are able to understand what I'm trying to say here. So I have a BA string. So I have a string like this, some asterisks, then some A's, then some asterisks, A, asterisk, A, something like that, right? Now what happens is that in every asterisk I can place any amount of B from 0 to K, right? So if I have a consecutive chain of asterisks like this, then it doesn't make any sense to consider every particular consecutive asterisk separately, right? It doesn't make any sense to like consider every star separately, and the reason for that is that in this particular region I can place the number of bees starting from 0 to 4k because there are 4 stars here, right? So it doesn't make sense to consider every star separately and say that this in this region I can place 0 to k, then in this region I can again place 0 to k, so on and so forth. It makes sense to just consider all of these 4 together and say that I can place I can place bees from 0 to 4k here. Similarly, I can place 0 to 3k bees here. I can place 0 to k bees here, and again 0 to 3k bees here, right? So uh, it seems relevant to just replace these asterisks, these consecutive asterisks, by their corresponding number of maximum number of bees that can be placed, right? So in the first region I can place 4k bees, then I have some A's, then I can place 3k bees, then I have some A's, then again I can place 3k bees, then I have some A's, something like this, right? So again these A's are just like a burden for me, right? So it makes sense to just remove all these A's and just focus on the consecutive amount of B's that we have here, right? So let's just remove all the A's here. So I have 4k, then some A's which I'm not writing down, then I can place 3k B's, then some A's which I'm not writing down. Sorry, this should be k. So 4k, 3k, yeah, 4k, 3k, k, and again 3k, right? Yeah, so that's what I have here. It should be a k, 4k, then 3a's, then 3k, then 3a's, then k, then 4a's, then 3k, then 3. Yeah, so yeah, I'm just removing all the a's, and I'm left with these consecutive segments, right? In the first segment I can place anywhere from 0 to 4k bees. In the second segment I can place anywhere from 0 to 3k bees, so on and so forth, right? Now now again I need to output the xth lexicographically minimal string, and for a string to be lexicographically minimal I have to minimize the leftmost element. I need to minimize my leftmost element, right? It is always beneficial for me to keep the leftmost element as small as possible. So if I have to go upwards lexicographically, then it makes sense to add bees starting from the right, right? So it is beneficial to start adding bees from the right, and the reason for that is I want lexicographically minimal xth string, and for a string to be lexicographically minimal I need to minimize its leftmost portion as much as I can, and I know that a b is always greater than an a, right? So it is always beneficial for me to keep as many a's as I can towards the left. So that's why if I'm adding a b, it is beneficial for me to add b's to the right. Okay, now let's see what happens. So if I need to find the lexicographically minimal string, that is x equals to 1, then it makes sense to just replace all these asterisks with nothing, right? I can just replace all these stars with nothing, and I'll be left with a few a's. Here I will be left with like 4 plus 3 plus 3 plus 1, 11 a's, and that will be the lexicographically minimal string, right? So if x is equals to 1, the string which I'll get is something like this: a, right? But if x is equals to 2, what happens is that now I need to insert exactly one b, and it makes sense to insert it as right as possible. So I'll insert a b here, and that gives me a, b, a. So this is the second most lexicographically smallest string. And again, if I want the third lexicographically smallest string, then I will just insert a b here. It's like I already had a b here, so I will insert another b here, and then I'll be left with a, 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 B, B, A, right? Yeah, so this is the third lexicographically smallest string, and for x equals to 4, I can just insert 3 b's here, and I will get something like this. Uh, Also, it makes sense to, I can just put at max 3k b's here, right? So for x equals to 4, I am putting 3 b's. So for x equals to, so I can just keep doing this, and for x equals to 3k plus 1, what I will have is that first I will put 3 a's, then an a, then 4 a's, then I will put 3k b's. So these are 3k b's, and then another 3a, right? So right now, until now, nothing is very bad here. I'm just linearly adding a b here, and my x is increasing by 1. But now what happens is that I have filled my maximum capacity of b's that I could have done here, and now I have to come here, right? So for x equals to 3k plus 2, what happens is that I will have to put a b here, and the rest of the string has to be lexicographically minimal, right? So I will just put nothing here. So that leaves me with a b a, right? So again, I'm starting with nothing here, and now I have put a b here, so I can just repeat the entire process and just put 1b, then 2b, then 3b, and up till 3k b's here, right? So I can just keep doing this. Again, how much time? I can do it for, so I already had 3k plus 1 strings, and I can again do a 3k plus 1 strings here. So I can do 3k plus 1 times 2, right? So using just this suffix, what I proved is that using just this suffix, I can have at most of 2 times 3k plus 1 strings, right? And using just this suffix, I can have 3k plus 1 strings. And I can just easily extend this observation, and I can do something like this. So coming back, the array which I had was something like this: 4k, 3k, k, and again 3k, right? So using this suffix, using the suffix number 1, so using last suffix, the number of strings that I got was 3k plus 1. Using second last suffix, so using the second last suffix, the number of strings that I have was 3k plus 1 times k plus 1, right? And using third last suffix, I can extend this observation, and the number of strings that I will get is 3k plus 1 times k plus 1 times 3k plus 1. And similarly, using the last suffix, the total number of different strings that can be formed is nothing but the product of all of them incremented by 1. So 3k plus 1 into k plus 1 into 3k plus 1 into 4k plus 1, right? Yeah, so this is how I'm going, and I hope up till now things are clear. So yeah, this is how I'm actually going here, and so if I just have to count the total number of strings that can be formed, these are nothing but this particular product, right? And I have been guaranteed that x is less than equals to the total number of strings that can be formed, so I know that x is less than equals to this particular number. So what happens is that now my task is to find the first particular index I, such that the total number of strings that can be formed using the suffix ending at I exceeds x. So I have to find the first index I such that number of strings that can be formed using the suffix I, using the suffix I to n, using the suffix I to the size of the vector that is forming. and the size is going to be nothing but the total number of continuous chunks of stars that I'm getting, right? So I have to find the first particular index such that the total number of strings that can be formed exceeds x, right? So if I find such an index, I know that every asterisk to the left of it is useless. I have to just leave it as it is and not insert any b here, right? So every asterisk to the left of the index will have 0 b's, right? So here let's say that so let's look at the test example here. So let's look at this last example, right? 6 3 20, and the string which we have is star star a star star star, right? Yeah, so the corresponding vector that we will get here is of 2k and 3k, which is nothing but for k is equals to 3 we have what, 6 and 9, right? So we have a vector like this. Now the number of strings, let us denote by prod of I. So let us denote by prod of I the number of strings formed from the prefix I. So here we can easily see that prod of 2 is nothing but 10, and prod of 1 is equals to 10 into 7, which is equal to 70. So total number of strings that can be formed here is nothing but 70. And according to the problem, I have to find the 20th string, right? So the index where 20 exceeds, the index which exceeds 20 is nothing but 1. So I have found out that the index is 1. But let's say instead of 20, I had to find the fifth lexicographically smallest string. In that case, my index, the first index which exceeds x would have been the index 2. And I could have said that all the asterisks in this particular chunk 1 are filled with 0 b's. So I can just say that all these asterisks are useless because I'm not putting any b's here, and only the only useful asterisks are this ones, right? So yeah, I hope this is clear enough. So once I have found the first index, let's see what happens. So I have found the first index, and I have also maintained prod values, right? So I am at an index I. Yeah, I am at index I, and I know that prod of I is greater than equals to x, right? So how do I decide the total number of bees that I have to place here? I know that if I place k bees, then that is sufficient for me, and the reason for that is that prod of I is greater than equals to x. So all that means is that if I put if I put the maximum amount of bees that I can in this position, then I will be satisfied. Then the total number of strings will exceed x. So I don't have to worry about any constraints here. I just need to decide actually how many amount of bees do I need to place here, right? So let's see. So let's say if I place, let's say PBs, what happens is that, so if I place PBs, the number of strings formed is what? So I'm placing PBs, right? So the number of strings which will be formed is nothing but prod I plus 1 multiplied by P plus 1. Again, pay attention why this is happening. So if I was putting 0 b's, then the total number of strings which were formed were nothing but prod of I plus 1, right? So now I'm placing 1 b, then the total number of strings which will be formed will be double of that, right? Because I can just repeat everything. And similarly, if I'm placing 2 b's, then the total number of strings will be 3 times prod of I plus 1, right? So if I'm placing p b's, then the total number of strings which will be formed will be p plus 1 times prod of I plus 1. So I need to find the smallest value of p. So I need to find the smallest p such that prod of I plus 1 multiplied by p plus 1 is greater than equals to x. And this is nothing but ceiling of x upon prod of I plus 1, right? So all I need to find is ceiling of x upon prod of I plus 1 minus 1, right? That will be my p, right? So if I find the ceiling of x upon prod of I plus 1, I will get p plus 1, and I can just subtract 1 from it. So that will give me p, and so I have successfully found out the total number of b's that I need to place at the index I. Now what happens is that I can just repeat this process for all the indices which are greater than I. So repeat the same process for all indices greater than I, right? And in this way, I'm doing everything avoiding any kinds of overflows, right? The main challenge in this problem was to avoid overflows, and the reason for that is that this particular product can be very, very huge, right? Because I know that k is up to 2000, so this product can very easily overflow, and we can't just naively do things here. So that is why we need to go from the right and find the first index where this product is exceeding x, and then we can easily find out the total number of b's that we'll have to place here, right? Great. So this is how we are going to work, and we'll go once we find out the first index, we can easily figure out the total number of b's that we need to place at that index, and then we can repeat the process to all the indices which are greater than my index without worrying about the total number of b's that can be put are sufficient or not, because I'm sure they will be sufficient, right? So this is it for problem C. Enough explanation. Now it might not be very, very clear right now, but let's have a look at the code, which is again a bit complicated, but I'm sure it will make things easier to understand. Right. So first of all, what I'm doing is that if I find an asterisk, I'm going as right as possible, and as long as I keep getting asterisks, I'm continuing my chunk, and I count the total number of asterisks that I'm getting, and then I push back in my vector count times k. So that is nothing but the total number of b's that I can put, right? So I'm basically grouping all the consecutive asterisks together, and in my vector, I am just pushing back the total number of b's that can be put in place of all these stars. Right, so once I have my vector prepared, I'm just taking another vector of answers, where answer of I stores that in the particular position I have to replace the asterisks with how many b's, right? And the size of this vector is nothing but the total number of continuous chunks of stars that I'm getting. And then I also have this product, where product of I is nothing but the total number of strings that can be formed from the suffix of I. And first of all, I'm finding the index. I'm finding the first index from the right, such that the total number of strings that can be formed from the suffix of the index exceeds x. And let's see how I'm doing that. I am doing that from a separate function. Yeah, so I'm going from the right, and in a particular index, I know that I can put from 0 to ai total number of b's, right? I know that ai is the maximum number of b's that can be put, and also I can put 0 to ai b's, right? So I'm iterating from 1 to ai plus 1, and if prod into it exceeds the value x that I have, prod is nothing but product of I plus 1. I am maintaining this in a single variable. So if prod into it is the total number of b's I am putting minus 1, plus 1, right? So it is the total number of b's I am putting plus 1. So it is nothing but p plus 1. So if p plus 1 into prod of I plus 1 exceeds the value x, then I know that the answer will be ceiling of x by prod minus 1. And this is exactly what's happening. And also I am decrementing x by prod into answer of I. Again, this is natural because I have to bring down x from x to 1, right? So once I have brought x to 1, I can just end the process, right? So yeah, I am decrementing x by product of I plus 1 multiplied by the total number of b's that I'm putting here, because that is the total number of strings which will be left with me now. Cool. Yeah, makes sense. Right. So then I'm finally returning I, and I is the index where the first time the product is becoming greater than x, right? And if that is not happening, if that is never happening, then I just maintain my product, which is nothing but I'm multiplying product by ai plus 1, and I keep doing that. Product of I becomes prod. So basically I'm maintaining the product array in this function, and I'm also calculating the first index where the total number of strings that can be formed exceeds my value x from the right. Right, I hope this makes sense, and I hope this line of decrementing x also makes sense, right? Yeah, so this is essentially it for finding the first index, right? I am doing answer of I as the ceiling of x by prod minus 1. yeah, so this is it. And I'm decrementing x by product of I plus 1 multiplied by the total number of b's I'm placing. And this can be understood like this. So if I place 1b, then I'm decrementing x by product into 1. And the reason for that is that I'm placing 1b. So what that means is that I have already put all the elements which were before it, right? So I have to now start from the beginning. So that is why I'm decrementing x by product of I plus 1 multiplied by the total number of b's that I'm placing here. Great. So now, yeah, I have found the first index, and now there is nothing to worry. Now I can just go from that index down to the size minus 1, and I can just repeat the same thing, essentially the same thing. Now I don't need to put any if conditions here, and I can simply do something like this. Answer of I is equals to ceiling of x by prod minus 1, and I can again decrement x by answer of I multiplied by product of I plus 1. And I can keep doing it, and now I successfully have my answer vector. The only thing which is left now is to construct the string back again, and that can be done very easily using something like 2 pointers, which I'm doing here. So initially j is 0. So again I iterate for my string starting from 0. As soon as I find a star, I'm going to put the total number. In my answer of j, I know the total number of b's that I'm putting at that position. So going from 1 to answer of j, I increment b to my string, and then I increment my value j as one does in a basic 2-pointer approach. And yeah, this is exactly what's happening. Otherwise, if s of I is not star, then obviously I'm just adding an a to my answer string, right? So yeah, this is it for problem C. Again, I know this is a very complicated approach, but I have tried my best to make it as clear as possible. So yeah, I hope you guys were able to understand this, and if not, I recommend you to watch it again, right? So yeah, this virtually completes the solution to problem C. Now let's move on to the next problem, problem D. Okay, now this is a basic maths problem. Let's see what's happening here. So you have an array A of n integers. N can be only up to 100, and the values of ai can be huge, from 1 to 10 raised by 9. And you have coins only of denominations 1, 2, and 3. And what you want is you need to minimize the total number of coins you need to take, such that using these coins you can buy every item precisely, right? You have to buy just one item, but you don't know which item you need to buy. So your coins should be such that you can buy every item. You can just pick any random item and buy it, and you can have the exact change for that amount, right? So you need to pick any random I, and you have to be sure that if you pick ai, then you can construct ai using your coins that you have. So you need to output the total minimum number of coins that you need to achieve that goal. So there is just one very simple observation in this problem. Right. So let's write down our goal first. Our goal is that we need to minimize the total number of coins such that if we pick any random index I, we have a way to construct exactly ai using our coins, right? So this is our goal, and we'll start with 3 observations. So observation 1 is that it is never optimal to take more than 2 coins of denomination 1. And let's see why that is happening. So let's say we pick three coins of denomination 1, right? So if we do that, what is the total amount that we can form? What are the total different amounts that we can form? We can form 1, we can form 2, we can form 3, but we cannot form anything else, right? We can, using these 3 coins, we can just form a 1, a 2, and a 3, right? But if we replace this with denominations 1, 2, and 3, Now that increases the range of amounts that we can form. We can form 1, 2, 3, 4, 5 and also 6, which is strictly better, right? So this is strictly better than this. And this is the reason it is never optimal to take 3 ones. We can replace all the 3 ones by just 1, 2 and 3, and we can form strictly better amounts of money, right? So this is observation 1, and it is pretty easily proved as well. Observation 2 is again similar. So it is never optimal to take more than 2 coins of denomination 2. And again, let's say we have 3 coins of denomination 2. The total different amounts that we can form are 2, 4, 6 and nothing else, right? If we pick any coins, we cannot make anything other than 2, 4 and 6. But again, if we replace it by 1, 2, 3, we will form 1, 2, 3, 4, 5, 6. And this is again strictly better, right? So this is proof that it is never optimal to take more than 2 twos as well. So yeah, and these two observations are pretty much very, very crucial. And the third observation is that if m is the max value in the array, then it is never optimal to take more than m by 3 coins of denomination 3, right? It is never optimal to take more than m by 3 coins of denomination 3, and the reason for that is that it is just going to waste, like the leftover coins are just going to waste. And I mean, it is very easy to see, because if we take more than m by 3 coins where m is the maximum value, then the total amount of money that we are making exceeds the maximum value, and that is essentially useless for us, right? So that is of no use. So the third observation is also very easy to see. And using these 3 observations, now I have pretty much solved the problem. And what I can do is I can just iterate over the number of ones that I'm taking. I can take ones starting from 0 to 2, and also I can iterate over the number of twos that I'm taking. That also goes from 0 to 2. So it just keeps the things O of 1. And now talking about the threes, right? So the number of threes that will make number of threes that I will take is nothing but it will go from m minus 4 to m, right? And m minus 4, it will be m minus 4 when I'm taking 2 coins of denomination 1 and 2 coins of denomination 2, and it might be even greater than m minus 4. But just to be safe, you can take the minimum amount of minimum amount of 3 denomination coins to be m minus 4, and you can iterate from m minus 4 to m, and that will be it. So now the only task left is to check whether you can satisfy all the conditions using the particular coins that you have taken. And again, that is also not a very difficult thing. Let's just have a look at the code to see how I'm doing that. Yeah. So it's basically just brute force. Once you have observed that you don't need more than 2 ones and more than 2 twos, so you go from you iterate your ones from 0 to 2, you iterate your twos from 0 to 2. Also, max 3 is the max element by 3, right? So you iterate your 3 from max 3 minus 4 to max 3, and right. So now when you are at a particular value of 1s, 2s and 3s, the total number of coins that you are taking are 1s plus 2s plus 3s, right? And now you need to check whether there is a way to satisfy your conditions for all the coins or not. So let's see how we are checking that. So I'm iterating over all the items that I have, the prices of all the items from 1 to n, and then I'm saying that I use x once and I use y twos. Obviously I cannot take more than ones once and more than twos twos, right? So I'm iterating my x from 0 to 1s, and I'm iterating my y from 0 to 2s. So if I'm taking x once and y twos, then the amount that I'm making is x plus 2y. So I will just subtract them. I'll just subtract that from ai, and what I'll be left with is ai minus x minus 2y. Now the condition to be satisfied is that this left should be greater than equals to 0. It should be divisible by 3, and the number of 3 rupee coins that I have should be sufficient to form this amount. And what that means is that left by 3 should be less than equals to the total number of 3s that I'm taking, right? And if that is the case, then I will say that I have found a valid match. And if I have not found a valid match, then I can just do OK equals to false. And what that means is that I will not be able to make the ith currency. I'll not be able to make the ith item exactly, and so my okay will be false. So finally, if I am okay, that means that using these amount of coins, I have successfully made all the items exactly, right? So I can just say answer equals to minimum and coins. And if I do that, finally I will be left with the correct answer. And yeah, this pretty much sums it up. This is the complete solution to problem D, right? That's why I was saying that problem C was difficult than both D and E. And we'll come to E now, which I thought was even easier than D. But yeah, let's come to problem E now. I hope problem D was clear enough. Okay, so this is a very sweet problem. We have an array of integers and we have to perform Q queries. And the queries can be of two types. In the queries of the first type, initially we have an empty sequence, so we have to append x to the end of the sequence. And in a query of the second type, what we need to do is we need to go through the entire sequence and replace all the occurrences of x with the value y. Essentially, this is what we have to do. And after we have performed all the queries, we have to find the resulting sequence after performing all the queries. And yeah, this is all that we need to do. A very short and simple problem statement here, right? So yeah, let's see how we are solving this. This problem can be solved with a very simple observation. And if you were able to do it in the contest, I'm sure that you would have actually solved this problem. So let's see what happens. Let's look at a particular element x. So I have a few occurrences of x here, right? And let's say I have two operations concerning x, right? So I have two operations of type 2 concerning x. So one operation is 2xy, and then to the right is one operation 2xz, right? So I have a situation like this, and here what I claim is for any x, I have to give priority to the leftmost operation of type 2 concerning x, right? So the leftmost operation of type 2 concerning x is nothing but this particular observation, this particular operation, right? So what I have to do here is that I have to give priority to this operation, and the reason for that is that I'm going from left to right. Once I get to this operation, all these x's will be converted to y's, right? And now this operation will search for x's, but these are all y's, right? And since these are all y's, this second operation will be virtually not affect any x in this particular region. But if there is an x in this particular region, then this operation is going to affect this x, right? Because then for all these x, these are the leftmost operation of type 2 to the right of the x, right? So yeah, that's the thing we have to do. But this is not a very convenient situation for us. Why? Because if we try to naively do this, then that will take linear time for each query of type 2, and we don't want that because the number of queries is very huge. So a linear time for any query will definitely be a time limit exceeded for us, right? So what to do here? So what happens is that since we are giving priority to the leftmost element, it is a very inconvenient thing for us, right? But what happens if we process the queries in reverse order? Let's see what will happen if we process all the queries in reverse order. So now, first we have a query of type 2xz, then we have some x's, then we have a query of the type 2xy, and then we have some x's. And now this is a very, very convenient situation for us, right? Why? Because once we encounter this query of the type 2xz, we know that any x has to be replaced with z, right? So I will just replace all these x's with z, going from left to right. I don't have to go back to any previous positions here. And now I hit this second query, and I know that any x has to be replaced with y. So I will just go to the right. If I find any x, I will replace it with the y. So this becomes very, very convenient and simple. So now I can just linearly iterate and do all the operations in O of n time. Finally, reverse the sequence and print it. Right? This is basically it. You can just go in reverse order and you can just maintain for each element. You have to maintain. Also, one thing which I missed is that we will have to maintain a vector actual of I, where actual of I, so actual of I will store the actual value by which we are currently representing the number I. Right? So yeah, essentially this is what is happening. So let's see what happens here in this particular question. So in this particular sequence of queries, I have already reversed the queries, so I'm processing them in reverse order. So what happens is that I get a query of the form 2xz. So what I realize is that I'm representing z not with z but actual of z, right? So I have to replace all these x's with actual of z, not z. Similarly, I am representing y, so I have to, according to this query, I have to change x to y. But I know that I am representing y by actual of y, so I will just replace all these x's with actual of x's, and that will do the job for me. So yeah, this is basically it. If I encounter a query of type 1, I will just push back into my sequence actual of x, and if I encounter a query of type 2, all that I have to do is I'll just replace actual of x by actual of y, and that will do the job for me. So this is essentially the solution to problem B. You iterate to problem E. You iterate everything in reverse order, and you maintain an actual vector where actual of I stores the actual value by which you are representing the number I currently. And if you find out a query of type 2 which says x comma z, then you will just say that actual of x is equals to actual of z. Otherwise, you will just push back actual of x into your sequence, and finally you have to reverse the sequence and output it. So this basically completes the solution to problem E. Let's have a look at the code now. Okay. So this is an MP vector, which is basically the actual vector that I was saying. Initially, every value is represented by itself. So MP of I is equals to I for all I from 1 to 5 E5. Then I am going to all the queries and I'm storing them in a vector. And finally, I am iterating this vector in reverse order, and I have this sequence, answer sequence with me. So if I get a query of type 1, then I will just push in my sequence the actual value of the element that is provided in the query. Otherwise, if I'm getting a query of type 2, I will change the actual value of x to the actual value of y, where x is ai1 and y is ai2. So I have my sequence ready with me. Finally, I will just reverse the sequence and output it. I'm reversing it because I'm processing all the queries in reverse order, right? So yeah, this basically completes the solution to problem E. And that is all that I had planned for today. So yeah, this completes the video today, and thank you for watching till the end, and I'll see you in the next one.